in this section, we're going to talk about how we're going to define shear flow for arbitrary cross-section. So what this means by arbitrary cross-section is the thickness of the tube can vary and the radius of the tube could vary. So it doesn't have necessarily a circular section anymore. All right. So if we looked at, so if we took a small element along the length of our tube that we had an applied torque along, and we enlarged it, we could define we can define 2 points. We can define point 1 and we can define point 2. At point 1, we have a shear stress tau 1, and we have a shear stress and a thickness of T1. At point 2, we have a shear stress T2 and a thickness, shear stress tau 2 and a thickness of T2. All right, so we can define point S, we can define that as being at a location S along the perimeter of our circle. So you can think about if we started our perimeter here, we went all the way around our circle. All right, the start of the perimeter would be 0, and the end of the perimeter for a circular section would be equal to 2 pi r. Okay, so we're going to be at some arbitrary point on our tube, which we'll label S. So S goes from the start of the perimeter to the end of the perimeter. So for a circle, it would be 2 pi r. All right, but we're doing it for an arbitrary section, so we're just going to use S. Okay, so we can define T1, or tau 1, and T1 and tau 2 and T2 using functions by saying the shear stress is a function of S, okay, or the function of its location along the perimeter. All right, and we can do that for T2 as well. Okay, so if we look at our element here, and we balance the forces along the x-axis, what we end up getting is we'll take our shear stresses and we'll multiply them by the cross-sectional area on both sides. So on both the left-hand side, I guess the near side, and the right-hand side of the section, and then the dx terms will cancel out, and we're left with this equation here. Okay. Now, if you remember from the last page, we defined Q as being equal to the shear stress times the thickness. Okay, so based off of this definition, in order for our system or our element to be in equilibrium along the x-axis, our shear flow must be constant along the perimeter of the beam, or the perimeter of the section. So within a single closed well section, the shear flow must remain constant at any. So regardless of the location along the perimeter, the shear flow must be constant.